Hello everyone, welcome back to another GIS Mathematics lecture video. And in this lecture video, I want to continue our discussion on some sample equations for some sample map projections. And in this one, I want to talk about what we would call a conformal, cylindrical, normal map projection. Right, so this is something that preserves preserves shape. So in the first video discussion, we talked about something that preserved distance north-south. In the last video, we talked about how we can augment that equation to change the relationship between the calculation for northing and the calculation for easting so that the area of a shape was maintained. Now we're going to talk about something called conformal, which is where we're going to, again, augment that original equation so that the relationship between northing and easting is such that we maintain the shape of the shape. We call that conformal. And again, cylindrical, meaning that our developable surface we're going to keep as a cylinder. And then normal, again, because we're going to have the cylinder running north-south. So the standard line would be the equator. So let's go ahead and just quickly look at what we've done before. So in the original equation, right, we had our easting was equal to the radius of our reference globe times our latitude, times our longitude, and we had our northing equal to the radius of our Earth times our latitude. And we've already said that in this case, right, we have some distortion east-west because this really should be r cosine theta times lambda. Right, so we've basically introduced this error here equal to not having cosine of theta. And when we wanted to make it in a equivalent projection where we kept the area the same, we introduced this cosine theta into the northing and then we integrated. In this case, right, we wanted to maintain the shape. We're going to do something very similar, but instead of introducing a cosine theta into here, we're going to introduce a secant theta, and then we're going to integrate. So what we're going to say is that the northing in this case is going to be equal to the integral, right, again, this is the integration sign, of r. We're going to keep the theta over here. But rather than adding in cosine, we're going to add the secant of theta times theta. And then we're going to integrate based on theta. So again, I don't expect you to necessarily follow the integral calculus here, but I just want you to sort of understand that what we're doing here is we're introducing this secant theta to try to, again, adjust the ratio of easting and northing so that we end up preserving shape on the other side. So what's going to happen here, right, if we actually do this integration, right, we're going to end up with a northing equal to r. R keeps being maintained, but the sort of derivative of secant theta is going to be this mess called log base e, or this is also known as the natural log, or ln, natural log, of the tangent, keep things a little bit cleaner, of the tangent of pi over 4, because we're in radians, so this is going to be 45 degrees, plus theta, right, which is the latitude measured again in radians, over 2. Okay, so hopefully this makes sense. Again, this is just the integration of this. I don't necessarily expect you to know that. If you're interested in integral calculus, there are chapters of it available in the textbook. And then we have the easting. Again, we're going to keep as this r lambda. Right, so just like with the equivalent projection, right, we have done this whole business here to try to set up the ratio between easting and northing so that when we plot these things, right, we end up with a conformal, or we're preserving the shape. Hopefully that makes sense. If you have any questions, please reach out. Thank you.